Good morning, good afternoon, and good evening from Bulgaria. I'm Oleg Mushkarov, and I'm the director of the International Center for Mathematical Sciences. November 1st is a special day for all Bulgarians, because on this day we pay the tribute to the memory of the great Bulgarians, distant and close, builders of modern Bulgaria. The Bulgarian mathematical community is happy to celebrate this day with the consortium distinguished lectures of Professor Adiprasito. I was expecting that Professor Richard Stanley will introduce Karim. Unfortunately, he is not on Zoom, but Karim is so famous that I think we can start without any introduction. So, Karim, the floor is yours.
We're very happy to have today Karim Adiprasito, who is going to be a second speaker of this lecture of the consortium. And he is one of the hot stars in combinatorics and all related topics. In fact, it will be fair to say that he has made applying ideas of combinatorics to different parts of mathematics into an art. So we are very happy to hear Karim today. So, and let me lay on you, a friend of mine, a great scientist, and a great humanitarian, Karim Adiprasito. Karim?
A great humanitarian, I don't know. Okay, now we are getting a little bit into fantasy territory. All right, thanks for the introduction. I hope that Richard can join later. It would be nice if he can hear my talk. So what I want to talk about today is really somehow a story beyond algebraic geometry, but I will start out by talking about some very basic some combinatorial problems. I will reduce them to problems in algebraic geometry, and then it will turn out that algebraic geometry is actually inadequate. It's not, I mean, it's not powerful enough to handle it. And then I will introduce a method to get actually beyond what is known in algebraic geometry. And this will again use combinatorics. So here's the problem, and it's really very basic, and I really love it very much. It starts, okay, so I'm not very good with dates. With Euler and Descartes, I think Descartes was roughly 300 years ago, but correct me if I'm wrong. Anyway, at any point, interrupt me if I say something wrong historically or mathematically, or if you have a question. So the problem is as follows. At least somehow the way the formulation that that Descartes and Euler considered, and this is, let's say you have a planar graph without double edges and without loops. All right. Then you can ask yourself, well, how many streets can I draw? How many edges can I draw with a given number of vertices? Right. It's a very practical problem. You have some number of cities on the globe, and now you want to connect them by streets. You don't have any access to traffic lights, so crossings are not allowed. So how many can you draw? I mean, you don't want to be wasteful and connect a city by 2 streets, right? You don't want this, right? So, and you don't want to connect the city to itself, really. I mean, that's just waste of taxpayer money. So these things are not allowed. So this not allowed is, let me make this, right? We don't waste taxpayer money here. So how many can we draw? And the problem, okay, so you can be naive and just try out. So when you have 3 cities, okay, so then there are 3 edges, and then if you add another city, okay, then you can again connect to all the previous ones, and then maybe you build a 4th city somewhere, and then you see that, okay, so it seems that you cannot connect all of them together, all right? So not all of the cities can be drawn, so one is missing here. And this is indeed not a hard theorem to to establish, or not a hard situation to analyze, because, well, in the plane we know there are several nice properties. So we know, for instance, that the vertices minus the number of edges plus the number of triangles, if I have a triangulation, is equal to 2. And okay, so what I mean by triangulation, I mean by that every region here is a triangle. It's bounded by 3 edges. And what we also have is that if I take 2 times the number of edges, right, somehow, then this is equal to 3 times the number of triangles by counting edges and triangle pairs. That's a simple enough. These are 2 simple enough equations. And these actually apply to our situation, because whenever you have a drawing like that, all right, of cities and streets, then you can add some, you can greedily add some additional streets until every region is a triangle, right? If it wasn't somehow, if some region is not a triangle, all right, maybe it's a quadrangle, then you can of course add one of the diagonals, right? You can select which one, and then you're done, right? So there is you can always do that. So this applies, and then you conclude, okay, so now you do some calculations and you conclude that the number of edges, so the number of streets you can draw, is less than 3 times the number of vertices, with an additive error that I don't care about. Okay, so it's, I mean, let's not care about this because it will get to be a little bit technical later. So that's it. It's very simple inequality. It goes back to Descartes and Euler. All right, so really classical. And that's it. So what do we do? So we are mathematicians, so we always want to generalize these things. So graphs in higher dimensions, right? Well, that's the first question that you can always ask if you slept during a talk and you wake up and you want to sound smart in the last few minutes. Then here's a good question. You can also always ask, well, what about higher dimensions? Well, a graph into dimension 3 or higher dimension, it's kind of boring because you can always embed a graph into a higher dimensional space, right? By the way, it's somehow, I'm sorry for you only seeing my forehead, but then because there's some issue with my other tablet, so I have to use the same tablet for presentation as for video. Graphs into dimension 3 are boring. So what else? Well, we could look at simplificial complexes, right? So simplificial complex delta, and I could embed that into higher dimensional space. So for instance, I could look at the 2-dimensional simplificial complex into R3. It turns out that this question is kind of planar again, because if I look at the 2-dimensional complex in R3, then I can look at a node here and intersect it with a small sphere. All right, this is a 2-sphere. And then I'm again in the planar situation. So we kind of analyzed that already. It's not I mean, it's a nice question, but it's not the question that we really want to ask. The real question we want to ask is when really there's barely any intersection, right? And when is there barely any intersection, right? If the dimensions add up. So I want to say that I want to look at delta, a 2-dimensional complex, the 2 complex into R4. All right. Or in general, I want to look at delta, k-dimensional complex into R2D. All right, that's the interesting question. And now I want to ask, well, how many k-dimensional faces or simplices? All right, so this is just the same. It's just I give different names because You might know it under a different name. So phases are just the simplices of the simplification complex. Can delta have in terms of the number of, let's say, k minus one dimensional phases, right? So in the planar situation, we look at the number of edges in terms of the number of vertices. For two complex, we look at the number of triangles in terms of the number of edges. Right? That's it. Simplices. Or some other number, right? Or in terms of the number of vertices, whatever you want. Doesn't matter. And just to say, we actually don't solve that problem. So the problem is still open. So this is still open. In general, because topological embeddings are kind of hard. So topological embeddings, we first have to actually agree what the topological embedding is, what topological embeddings you allow. And so there were very few non-trivial results for the topological case. And I should highlight that some of the best results here is due to sum and parser. Let me not actually go into this. It's basically it's a little better than the trivial bound. So it's so the trivial bound would be that the number of k dimensional phases is less or equal to, let's say, c times a constant times the k minus one dimensional phases times the 0 dimensional phases. And basically what Parser showed is that here there is an alpha where alpha is strictly less than 1, but also strictly larger than 0. And actually, as k goes to, so actually it depends on k. So let me say that. So this is the best thing we know for the topological case, and it's really it seems that really topological methods are not really suitable to get a tight bound. Maybe because there are several issues. Let me go to them later. But let me focus on what we can actually prove. So here's something that we can do if we restrict this case. If we restrict this a little. So if we can control this embedding a little. So for instance, if delta embeds into R2D, or we can equivalently ask S to D, all right, the 2D sphere, in a PL way, then, so theorem, then we have that the number of k dimensional phases of delta is at most the number of k plus k minus one dimensional phases of delta times a factor of k plus 2. Right, and you see that if k equals 1, then actually what we have is that number of edges is less or equal to 3 times the number of vertices. Right, if k equals 2, you get the following nice inequality that the number of triangles in your simplification complex is at most 4 times the number of edges. So these are very nice and simple inequalities. So let me just state, so what is really needed here? So what we really need is a delta has to be extendable. So really, really needed is that delta has to be extendable, or to a triangulation of the ambient space of S2D. And I notice now, I'm sorry, see, but, of course, if I look at k-dimensional complexes, then I into 2k, right? I'm interested in half dimension. And here as well, sorry. That's the result. So now I want to tell you how one tackles this. All right. So assume that somehow we have this assumption, or maybe we have it implied, or we make this assumption. So it's implied, for instance, if the embedding is PL. So what can we do then? So if sigma is this triangulation of S to K, then we can associate an algebra to it. Is there a question? Oh, okay. An algebra to it. So let me give you two ways to think about this algebra. One would be the one that Richard really likes, and one would be the one that I kind of prefer because it's a little more intuitive and a little more visual. Let me start with my way. And sorry, I don't know whether Richard is here by now. I hope he isn't insulted. If not, it's good. What you can do, okay, so let's think of sigma as, let's think like a toric algebraic geometer. So then sigma, really, it should come from a fan. So a complete simplicial fan. All right, it's not always the case that we can realize this, but a complete simplicial fan, that's just a collection of simplicial cones covering the space. So I think of sigma really being as what I obtain if I intersect this fan with the unit sphere. All right, sigma is somehow identify these two objects. So this would be a fan in right, somehow sigma I would identify with a complete fan in R2k plus 1. All right. And okay, so let me just then discuss this a little. So then I could look at P of sigma. This is the algebra of cone-wise polynomials. Sorry, is there a question? Someone spoke. Okay. Cone-wise polynomials. All right. So these are these are the functions from R2k plus 1 to the reals that are polynomial on every cone, right? On every single one of these regions. I'm a polynomial and I'm continuous globally, right? So that's it. And then, okay, so this is as a vector space, it's infinite dimensional. So what I do then is I take A of sigma, which is the quotient of this P of sigma, modulo the ideal generated by the global linear functions. Okay, let me write it like this. So it's the ideal generated by global linear functions. This is the algebra that I'm interested in. So that's all good and nice. Here's a second way of formulating it. And this is, now we don't need the fan. What we do is instead we take the polynomial ring. All right, so R of X, where I have as many variables as I have vertices in my simplificial complex. And then what I do is I take R of sigma, which is R of X, modulo the ideal generated by the non-phases. So this is the ideal generated by those monomials x to the alpha, where alpha is not in, or let me just, okay, support of alpha is not in sigma. All right? It's a simple object. So this is essentially the analog of P of sigma. And then what I do to get A of sigma again, let me just do it this way, is that I take R of sigma and I mod out general position linear forms. So the system theta of dimension sigma plus 1 linear forms. Theta. And then again, this is a finite dimensional object. So here it is something that was often disregarded in commutative algebra, is that this object, or in combinatoric commutative algebra, is that this object really A of sigma, in any way I define it, it depends really on this linear system theta. Right? So these are really different things, and we really behave very differently. And similarly here, it depends on these global linear functions. So there is some geometry encoded to it that is somewhat subtle in behavior. So let me go and state some properties here. So here's, for instance, the theorem of Hoster. And this is that A of sigma is a Poincare duality algebra. Or if you prefer the commutative algebra version of saying it, it's a Goran-Channel. It's a Poincare duality algebra. All right, so what let me set set D equal to the dimension of sigma plus 1, then, or in this case 2k plus 1, right? Then that is that I look at this object A of sigma. Right, notice that this is graded, right? I started with a polynomial ring that is graded, and then I modded out some homogeneous ideal. So I keep a grading. So I can talk about degree. So I can now look at the degree D component of this, and this is isomorphic to the reals. Okay. And then, okay, so now I can also multiply to this fundamental class. I can take something in degree K, and to get it to be in degree D, I have to multiply with something in degree D minus K. All right, so degrees have to add up. And this goes to AD sigma. All right, and this is isomorphic to the reals again. And this bilinear form is perfect. This is perfect. In particular, and this is important, we have a very indirect isomorphism between these two spaces. All right, these two are isomorphic. That's the first fact. Second fact, I should see. I shouldn't use k here. Sorry, because I used k for something else. I am very sorry. I'm very bad with indices. Let me use I. All right. Okay. So that's the first result. Okay. So maybe you want to compute them. So maybe you want to know how large these spaces are. So there is a kind of complete description in general how to do this for sigma. But I mean, I don't want to be so fine. I don't want to really know the details about these numbers. So let me just compute some of them in a very rough way. So one thing I can always say is that, for instance, that AI is generated by the faces of dimension by the faces of dimension I-1. So the faces of cardinality I. Right, because these are the monomials of degree I, they generate my ring. I have to. I mean, there is something non-trivial here because I say that I'm basically generated by square free elements. But, okay, so there's something to check, but okay, this can be done. So let me just not go over this. So this is Fi-1 of sigma. Right, so this is so the dimension of this is similarly dimension. Okay, so now what I did, I gave you a number, I gave you the generators, right? I gave you the generating system. And this gives you an upper bound. By knowing the size of a generating system, you immediately get an upper bound. So let me give a lower bound, and you do it similarly, right? So the way that you would do it is you look at the you look at a generating system, and then you kind of give an estimate for the number of relations. So let me do this somehow. For instance, if I'm interested in the degree k+1 component of sigma, then I can look at, okay, so what are the generators? Well, these are the k-dimensional faces. Okay, so cardinality k+1 face simplices. And then I have to estimate the number of relations. Now, there are several ways of doing this calculation and thinking about this, but it's not so hard to show that this is actually k+1 times the number of k-1 dimensional faces. All right, that's useful. So these are two useful inequalities. And actually, I mean, I stated this in general for I, but I mean, of course, I could specialize to k here. All right. So this inequality is a little bit more complicated in general. So I immediately stated it for k+1 and k. But the upper inequality, I could just specialize. This holds in general for all I, but I specialize. Now, notice that now I have done something very nice because the inequality I want, right? I wanted the inequality fk less or equal to k+2 times fk -1. But now what I have to prove is that dimension of, well, a k of sigma is larger or equal to the dimension of a k+1 of sigma. Well, almost, right? I mean, almost, because I actually wanted this for delta. So it turns out that these equations here apply for delta as well. So these apply to delta. To delta as a subcomplex of sigma as well. So it's not hard to see. And so now, okay, so I wanted this for delta. So I want to really have this inequality for delta. All right, that's what I want, which is, I mean, kind of lucky and unlucky, because, I mean, it turns out that on the level of sigma, it's actually easy to show that AK of sigma and AK plus 1 of sigma, that these are actually isomorphic as vector spaces. All right, so these are actually of the same dimension. Why? Because, well, they are Poincare duals, right? So if I multiply, then I get a perfect pairing. So these are vector spaces of the same dimension. All right, so that's good. Okay, but I want it really. I mean, I wanted it. I really want it for delta. That's the whole goal of the game. So why would this inequality hold? So let me now go to classical algebraic geometry. So I want to now say that there's a classical algebraic geometry result that, at least in special cases, implies this. Okay, and this is the following result. So theorem, Hodge, Lefschetz, and Hodge-Riemann for, okay, so I'm not stating the completely general case. For, okay, so for let's say for smooth toric varieties, but I'm already a little more general than that, toric varieties, because my fans, for instance, they don't really necessarily have to be rational, and they don't really have to be unimodal either. So it's already a little more general than that. Fine. Okay, so here's the theorem. Okay, so if sigma is a complete fan, again, I restrict it to simplificial anyway, but let me actually say it. It's simplificial fan in RD, and L in A1 sigma. This is the class of a convex function. So the class of a convex linear convex function. All right. Then we have two theorems that go in tandem together, and they're kind of important to remember in tandem. And the first one is Hodge-Lefschetz. And this is that, okay, so I have this convex function. So what I do is I take my algebra A sigma from, and I want to look at it in, let me again not use K, but let me use I here because I use K for something else. I want to look at this space in degree I, and I know that the space in degree d minus I, that this is isomorphic, right? These two are isomorphic by Poincare duality. These are the same vector spaces. But I want to more. I mean, this does not give me really an isomorphism directly. So I want a concrete isomorphism. So how would I write this down? All right. So one way, I mean, naturally, I could try to just do the multiplication with L, or with not quite. I have to I mean, multiplying with I would just get me to AI. With L, I would just get to degree I plus 1. So really what I want here is D minus 2I. All right. And this is an isomorphism. Okay, that's the first result. And second, now that I have this, I can define a non-degenerate quadratic form. This is usually denoted by QL. I wanted to give a name, so these are the Hodge-Riemann relations now. QLI, and this, and now what I do is I go from, well, I want to define a quadratic form on AI times AI to AD, isomorphic, right? Isomorphic to the reals. And what I do is I take A and B and send them to A times B times, and now I want to go to degree D, so I have to take L to the D minus 2I. Right? What the Lefschetz says is that this quadratic form is not degenerate. But I want more, right? I want a little more, so I want to say that this Hodge-Riemann relations, they should really give me some more information. So here's something I can define a subspace PLAI of sigma, and this is the kernel of the following multiplication. This is so kernel of the following map. I go from AI via the Lefschetz map L to the D minus 2I, but now I made a sign error, and for some reason I multiply once more. All right, it's what's this sign error? An index error, right? Multiplied once too many, and then I end up not in D minus I, but in D minus I plus 1 sigma. Now this is not necessarily an isomorphism anymore. This might have kernel, and if it has kernel, well, I mean, then I can define this as a kernel. And the point is that the Hodge-Riemann relations, so the Hodge-Riemann relations, they state that this QLI is definite of sine minus 1 to the I on this space PL. All right, that's it. Okay. So far so good. That is nice. So this is a tremendously important theorem, and so let me give some applications. Right. So some applications of this. Well, I mean, for instance, Stanley used this to prove half of the G theorem. Stanley, this implies half of the G theorem, so of the G theorem, meaning it gives you the necessary conditions for base numbers of polytops. So for polytops gives you, I mean, i.e. gives necessary conditions on what the phase numbers of polytops can look like. Right, so he looks at the vertices, the edges, the triangles of a simplificial polytop, and he wants to describe what kind of conditions these numbers have to satisfy. Right, how are they related? And it turns out the Lefschetz theorem gives this. So this is Lefschetz. So this is an application of Lefschetz. A recent, let me note that Hodge-Riemann also has an application. So Hodge-Riemann you should think of as a kind of generalization of the of Alexander Fencher. Right. So in fact, there's more you can can think of this really small. They are really connected. So there's a nice work of Kovansky and Tessier. These are related to Alexander Fenchel. Relate them to Alexander Fenchel. Relate Hodge to Alexander Fenchel. So this is something that the convex geometers are wrong, you know. It's not so important. And in particular, they also, the Hodge relations, they imply other things as well. So for instance, this Lefschetz, this result also applies to, for instance, Blockmann fans. So result applies to Blockmann fans. To fans over matroids. And there it implies, for instance, the log-concavity of the characteristic polynomial. Log-concavity of the coefficients of the characteristic polynomials. Coefficients of characteristic polynomials. Right? So that's all good. I mean, so that's an amazing. These are amazingly strong. Let me also now go back to the classical to the question that we discussed. Right. So we have a sigma. We looked at this in degree k. Now I don't. I mean, I already said that a sigma and ak plus one has ak plus one of sigma, that they are isomorphic. Right. So what? What does that help me? But now I have a stronger isomorphism, right? So I can write down that this isomorphism is induced if I am in this situation where this theorem applies. So there are several non-trivial things. So if sigma comes from a complete fan and L exists, right? L must be the class of a convex function. So there must be a convex function supported on this fan. If this exists, then I have this isomorphism directly, all right? Under conditions on sigma, I have this isomorphism, all right? Now, I also can look at the quotient to A of delta. All right, so this is a subcomplex. So if you think about this, right, I mean, as a subfan, it's just a restriction map. And if I think about this in terms of this the second definition, the phase ring definition or standard ring definition, then also it's just a subcomplex. And so I have I take out a larger ideal, right? So the ideal of non-phases just becomes larger, and that's it. There's something in chat. So there's a K here. Did you just ask this? I did not see this in the chat. I think it's simpler if either someone alerts me to questions in the chat, or you turn off your mute, or you turn on your microphone and just ask me directly. Sorry, I did not see this until now. I don't actually see when this was asked. So AK of delta, so AK plus 1 of delta. And then I have the surjection. Yeah, so I have an isomorphism. I have the surjections down here, so meaning that the induced map here is a surjection. So, and is surjective. All right, but the surjection implies the dimension inequality. Surjection implies the dimension inequality that we wanted. All right, so the dimension inequality again was that AK of delta as a vector space should be larger or equal to, it should be larger than AK plus 1 of delta, right? And so if I have Lefschetz, then I'm fine. I can solve it. Problem. All right, so now here's a kind of, I say most, this is a problem most of the time, in the sense that if I pick a random simplificial complex delta, or a random triangulation of a sphere sigma, this will not be a triangulation that can ever satisfy the conditions for this theorem, right, for the classical theorem to hold. So for most sigma delta, the conditions for the classical Lefschetz or Riemann are never met. All right. So, I mean, what most here means is, I can say, for instance, if I take a triangulation of the three sphere on n vertices uniformly at random, right? So I look at all the triangulations of three spheres on n vertices, where n is sufficiently large, then asymptotically, almost surely, this will not be coming from the boundary of a polytope, or in particular, it will not come from a complete fan which supports a convex function. So this is a result by Nuga-Alon and in parallel by Goodman-Pollack. All right, so this is a classical result. And that really ruins my day here for the moment, right? I cannot I cannot get around that. I cannot apply this theorem. So what do I do instead? And this is now where we go beyond algebraic geometry. So here's a theorem. Yeah, let me state the theorem first in its most general form. So actually, I will not state the most general form today. Today I will state the form that kind of most closely resembles the form that I just the classical form. And then tomorrow I will go more generally to things like sheaves over posets, which allows me to say additional theorems about, for instance, about lattice polytopes and H star vectors if you're interested in this kind of. But for now, let me just restrict. Okay, so let me just try to be as similar, as analogous to the other version as possible. So sigma is triangulated d-dimensional sphere, d-1 sphere. Right, I wanted d to be the dimension of the sphere plus 1. And here, this is somehow triangulated sphere is really in the most general sense. Okay, so so this could be a homology sphere. Homology sphere. And it might not even be a homology sphere. It might be just a homology manifold, right? That has that globally has a homology of a sphere. So it might not even be a manifold. Or homology manifolds. It's kind of a mouthful, so it's a homology manifold with a homology of a sphere. Homology of a sphere. Of a sphere. And here I'm stating this with respect to a given field. So K, let me say K a given field. All right, let me assume that the field is infinite. All right. So now I can look at A of sigma. And here I will define it. I take A of sigma as defined over K. All right. It's the same construction. I just take instead of starting with the polynomial ring over the reals, I start with the polynomial ring over K. Everything else is the same. And I notice that, let me index this. This is indexed by theta. Remember that this depends on theta. Then A of theta for generic theta. And L in A1 of sigma generic satisfies. Okay, so now let me state 3 theorems or 3 properties. And the first is just the analog of the Lefschetz, so hard Lefschetz. And this is really just the same thing, AI of sigma to a d minus I of sigma. All right, this is an isomorphism. So, how do I do it? It's L to the d minus 2R. Right? Good and nice. It's just the same as before, hard Lefschetz. Now I have something that replaces all Riemann relations. So all Laman relations. And this is the following. So I can again look at this bilinear form QLI. All right. So you remember this from before. It's the same bilinear form. All right. It's again just I take an element A in degree I and an element B in degree I, and I multiply them until they are in degree D. And for this, I need to kind of push them a little with L to the d minus 2I. That's it. So what is special about this? Well, this here is non-degenerate. When restricted to any square-free monomial ideal. So basically, I'm saying instead of saying something about the signature at a certain subspace, I look at many subspaces and say that this pairing does not degenerate. And in fact, I can say something a little small. So let me, before I say something stronger, let me just say that now, what are square-free monomial ideals? Well, these are just ideals of the form. I look at A of sigma, and I look at the subcomplex A of delta, and I look at the kernel of this map. All right, so these ideals. So these are the ideals I'm looking at. All right. So that's kind of a weird property. I will kind of explain it for a few seconds after I give the I say a little bit about more general versions here, or not more general versions, but some other interesting forms. So this is the original. So this is what I proved in 2018, and then two Greek mathematicians, they did something amazing. They basically said, okay, you are restricting to certain ideals. That's kind of boring. Why don't we take all ideals? Perhaps it works in all ideals. And indeed, somehow, amazingly, that's true. So at least in a slightly restricted sense. So here's something that so if characteristic of K is equal to 2, then there exists a field extension. There exists K tilde extending K, such that Q L I, right, over, so now I look at K tilde, and K tilde and sigma, and with a generic system, let me just make clear that this is also defined over K tilde, small K tilde, theta tilde, this is of parameters, a system of linear forms, such that this it never degenerates at any subspace. So this is totally anisotropic. The same thing is to say that if I take any u for all u in a I of sigma, what it says is that Q L I of u applied, u with u itself, this is not zero. That's a kind of amazing result, right? So it's never zero. All right, so all good and nice. And now let me say that, okay, so this is open in general characteristics. So this was done by Papadakis and Petrotou in 2020. It's an amazing result. So I think they basically found this by accident, so that this exists in characteristic 2 by basically just searching from Macaulay, somehow trying to understand some equations that they got out of Macaulay. And then in 2000, not write out the names, APP in 2021. So we gave a more general theorem. Let me not state the more general theorems now in full today, but let me just say that, so this is for general K, for general characteristic, we have a statement that is small, slightly technical statement that is strictly between the whole Laman relations, and this total anisotropy. So we don't know that QLI applied to any form with itself is non-trivial, but we know that either QLI U is non-trivial, or QLI U prime is non-trivial, where U prime basically has the same support, the same monomial support, right? It has the same monomials, but the coefficients change. That's it. Is non-zero. So this is some of this weaker version, and we don't know. Anisotropy is not known. Total anisotropy is not known. All right, I think I'm kind of over time now. I think we will continue tomorrow at the same time, but so let me stop here. So this is the theorem. Tomorrow I will slightly go more general. So let me say thanks for listening, and also thanks for having me. Actually, I don't know whether I said it at the start. Thanks. And tomorrow we will continue, and I will explain how these theorems are proven. I will go a little more general than this theorem in the stated form, and I will give you some interesting recent progress. All right. Thank you.
Okay. Thank you very much. So, are there any questions? Some remarks or comments? Okay, thank you very much again, Karim. And we start tomorrow at the same time.
Yeah, okay.
Yeah. Thank you very much.
Hi, Richard. Hi, Ilya. I don't see you, but I assume that you're... Yeah. Yeah, some people I know in the audience.
Yeah.
Okay, good. Bye. See you tomorrow. Thank you.
See you tomorrow.